Hello, everyone. We are Isaac Christensen, Michael Tomer, Daniel Nelson, and myself, Alex Guyman. We are from the Department of Electrical and Computer Engineering at the University of Utah, and we have designed a battery management system using our VLSI principles that we've learned in a class this semester.
Lithium-ion batteries are the de facto standard battery type you can use today. They provide high power output that lasts, and you'll find them in everything from laptops to electric vehicles. Unfortunately, they also have some safety concern. Modern lithium-ion batteries use liquid electrolyte to transmit lithium ions between the anode and cathode. The electrolyte inside is flammable, and if a battery cell is charged too quickly, it can cause a short circuit leading to explosions and fires. You'll run into this if you ever go for a flight. They want all devices with a lithium-ion battery to be with you in your carry-on luggage and not in your checked bags. This is because the pressure difference in the cargo hold can trigger problems. So with great power comes great responsibility to ensure your project's batteries are in a good state. When your project is checking power, voltage, and current for one battery, the barrier for using lithium-ion battery is not too great. But unfortunately, one battery alone sometimes will not suffice to power your project. That leaves you to have to run multiple cells in parallel or series and querying all of their state and health values by themselves. This problem presents a large overhead and a high barrier of entry for projects. This is where our project comes in.
Our Battery Management Unit, or BMU, manages all of the state of health querying directly. In our design, we chose semi-arbitrarily to manage 4 cells, though it could be easily expanded to manage more. Our BMU provides a simple SPI interface to an external microcontroller. On this interface, the BMU acts as a client with the microcontroller querying for status. We also provide an extra pin to act as an interrupt signal to alert the microcontroller that there is something important it needs to see. Every cell receives a temperature sensor and a voltage/current sensor. These will provide the state of health information on every cell. The inputs and outputs of the battery are connected through a charge-discharge gate. This will allow the BMU to automatically disable charging or output if the state of health on the battery becomes critical.
Internally, we broke up our BMU into 4 distinct sections. First, we have the SPI client, which was done by Mike. Next, we have the register file, done by Alex, the SPI sensor, done by Daniel, and I created the internal logic. I'm Isaac. Splitting it up this way gave us some pretty good benefits of being able to test each part individually before we put them together, allowing our final step of integration to only have to test the integration rather than the functionality of each module individually.
The SPI interface presented to the external project uses a SPI mode 0. Data is sampled on the rising S clock and switched out on the falling S clock, and it receives a 4-bit address from the external project about which value it wants, and then sends that out through the MISO port.
The register file is where all our sensor values are stored. There are 2 separate read interfaces, one for direct connection to our SPI client and one for our internal logic. There is also a write interface for sensor data to be written into this file.
The sensor SPI interface is connected to all of the voltage and temperature sensors, and when told to do so by the internal logic, queries for values. Some of these sensors also require initialization. This module uses the same SPI mode 0 like our SPI client interface. Because it interacts with 2 different kinds of chips, it is intelligent enough to know the length of the transaction based on the address and will automatically switch between an address of 8 or 16 bits and data of 8 or 16 bits.
Our internal logic are the brains of the operation, if you could call it that. It's quite simple. All it really does is instructs the SPI sensor to ask each chip for its values. As it's parsing these values, it asserts the interrupt if any out-of-bounds values are found. If the battery voltage, for example, is exceeding the nominal parameters, it can first stop the charging of the battery and then inform the microcontroller that things are getting a little bit wonky. This helps ensure the safety of the project.
We synthesized each module by itself and tested that. We then reran each test bench against the module netlist before proceeding on to place and route. We immediately recognized the need and invested heavily in automating our build process. Our system completed all of these steps automatically, allowing us to quickly iterate on designs without having to manually rerun each step. This saved us a ton of time as we were working through problems.
A comparable product to our design would be a battery management monitor from Stateful Systems. This monitor board can track up to 12 cells. We chose 4 in our design because we wanted to keep it simple. We could easily expand to 12. The Stateful Systems option does have a 22 ohm shutoff resistor across the battery bus for doing passive balancing. This board must also be used in conjunction with a microcontroller. The control board works very similarly to our battery management unit. It uses CAN 2.0, commonly found in cars, to communicate. The master control board can also aggregate status from up to 64 of these products for a combined 768 cells. For smaller projects, our battery management unit stacks up well against this kind of competition.
In conclusion, we think we made a pretty acceptable battery management system. Though it can't support as many batteries as the competition, for a lot of small projects you don't need that kind of scalability. Apart from electric vehicles, most projects are going to be on the matter of a dozen at most cells, making our product more than capable, especially if used in parallel. This has been our project. Thank you.